Let's start. So, good afternoon, everyone. Welcome to our academic section. It's the final section of our summer school. I'm from National University, and this section will have two lectures. And each lecture will be 90 minutes, and the speaker is Okuma Professor Okuma, and this talk will be a combination of yesterday's talk. He will talk about the patch and skin effect and its application in non-Hermitian and non-equilbrium system. Let's welcome this speaker.
Sorry. Okay. So first, I'd like to thank the organizer for giving me this opportunity. I'm the VP of Kyushu Institute of Technology. Today, I'm going to talk about the topological physics of non-Hermitian skin effect and its application in non-equilbrium systems. The first part of today's talk is based on our paper, the non-Hermitian topological phenomena. Review. The collaborator is Professor Topological. And related conclusions are the points. Okay. So before starting the presentation, let me introduce myself. I have a PhD at the University of Tokyo, and after that, I stayed in Kyoto for 5 years. And now I'm at the Kyushu Institute of Technology. And actually, Kyushu is very close to Taiwan. It takes only maybe 2 hours by airplane, so I can recommend you. And my research interests are the points, the speech points at Barcode, and Magnon, and topology and Hermitian physics. And today I will focus on physics of topological physics and Hermitian physics. But actually, the physics of magnons are closely related to the Hermitian physics. I will introduce subject physics in terms of Bohr-Bogdan Hamiltonian in the second talk. Okay, so let's start the first talk. This is the outline to the first talk. First, I will introduce what is non-Hermitian physics and why I'm interested. And then I will introduce the non-Hermitian physics of non-Hermitian skin effect. And after that, I will briefly review the competition between the Hermitian topology and the Hermitian skin effect. The main topics are the last one, the topological origins of non-Hermitian scheme effects. Okay, so I will proceed to this non-Hermitian physics. The definition of non-Hermitian physics is quite simple. The physics described by non-Hermitian matrices. And maybe 99% of the non-Hermitian people are focusing on describing the open quantum or classical systems. Or if you're on this matter physicist, the self-energy part of the wave function are also the source of non-hermiticity. And one and two are closely related to each other. But personally, I am also interested in the bosonic Hamiltonian without and with dissipation. And interestingly, even without dissipation, the physics of bosonic systems are related to the non-Hermitian spectral theory. I will talk about it in the second lecture. And the typical example is antiparallel magnets. Okay, so I'm personally interested in such kind of physics. And so in the first talk, I will focus on the mathematical part. So I did not specify the concrete physical systems. And I'm only interested in the spectral theory of free non-Hermitian type Hamiltonian with discrete translation invariance. Okay, and in the second talk, I will discuss the application part, the dynamical instability also in BDG systems with dissipating situation. Okay, so in this slide, I summarize some properties of non-Hermitian matrices. Maybe the first one is very trivial. The eigenvalues can take a complex number. So the energy spectrum is open read in terms of the complex plane. By the way, sometimes real axis is taken in the one direction, but this is just a matter of space. And the second one is more non-trivial for Hermitian people. The Hermitian conjugate of a right eigenvector is not always equal to a left eigenvector. So here I define the right and left eigenvector in the following sense. In the following equation. And so this they are nothing but the Brun and kept eigenvector. So in a Hermitian case for the normal matrix, then the Brun and kept vectors are usually in the relation of Hermitian conjugation. But in non-normal matrix, which is non-Hermitian, then such a relation does not hold. Not always, but sometimes does not hold. And moreover, the Hamiltonian is not always diagonalizable. If the Hamiltonian is parameterized and the Hamiltonian is not diagonalizable at some parameter set, then such a parameter set is called exceptional point. And maybe you can find easily the paper about exceptional point in recent archive.
Excuse me. So if a system has linear symmetry, then does it guarantee that the volume will be always
Actually, the phase transition point in the symmetric breaking is described by the exceptional point. So not always at one point the Hamiltonian is not diagonal. And last property that today's main topic is the boundary sensitivity of the sensitivity of the spectrum against the boundary condition. Recently, in condensed matter community, it is called non-Hermitian skin effect. And also, in recent condensed matter physics, the interface between non-Hermiticity and topology are extensively studied. I think there are three papers that contain the main theme in recent archive. The first one is the exceptional points in momentum space. So the Broco Hamiltonian is not diagonalizable at some momentum. This is a kind of generalization of the Dirac and metal to the non-Hermitian case. And second one is maybe related to the paper. And the non-Hermitian topological classification was proposed by Oezo at the University of Tokyo. And this is a generalization of architectural topological classification. Then last one is non-Hermitian skin effect. And under the non-Hermitian skin effect, the Hermitian boundary correspondence generalized to non-Hermitian boundary correspondence. Okay, so this is the introduction part. And next I will introduce what is the non-Hermitian skin effect and why it is interesting. Before introducing the non-Hermitian skin effect, let me check the common knowledge in solid state physics. For if the metal is sufficiently large, we should expect its band properties to be unaffected by the detailed configuration of its surface. This is a course of solid state physics written by Ashok and Wani. So this sentence states that the boundary condition is not so important for bulk quantities. So under this assumption, one can achieve the useful boundary condition, and usually we choose the periodic boundary condition. And so under the periodic boundary condition, we can use the Fourier transform. So and move on to the momentum space picture, or also called the bound theory. So this is based on the Hermitian solid state physics. But other than the Hermiticity, such a statement can collapse. So actually, the OBC open boundary condition, OBC bound spectrum is one state entirely different from the one under the periodic boundary condition PBC. And correspondingly, the under the open boundary condition, the eigenspace can be localized, localized at some value. So, and Yamamoto one named such a behavior the non-Hermitian skin effect. They define the non-Hermitian scheme effect as the following phenomena. All the eigenstates of an open chain are found to be localized near the boundary. And such a behavior of when function is non-local wave due to the non-local wave nature of eigenstates. Here, block wave in the plane wave. So, and under the periodic boundary condition, the block wave still the eigenstate of the Hamiltonian. But maybe this is too strong statement because there can be extended states. So here I will define conventional non-Hermitian scheme effect as a phenomenon in which all of the eigenstates of one-dimensional open non-Hermitian Hamiltonian are localized near the boundary, where L is the system size. So this is the definition here. And maybe I think the simplest model of the non-Hermitian scheme effect is a pattern-based model without disorder. This model is quite simple. This is just near the neighbor one-dimensional Hawking Hamiltonian, hyperbolic Hamiltonian, and with asymmetrical. Here, the asymmetry is in the amplitude, not in the complex space. So this is not Hermitian in general. And the spectrum of non-Hermitian, the spectrum of Hadamard's model is very notable. Under the periodic boundary condition, the energy spectrum can be easily obtained by using the Fourier transform. So energy is parameterized by the crystal momentum K. This one. And this is actually the ellipse on the complex plane. So this is very easy calculation, but under the open boundary condition, the situation is completely changed. So by the way, the following technique is very important for the data part. So please remember it. I will introduce an imaginary gauge transformation defined by following equation here. Small I is not a pure imaginary, but a scientific story for that. And so this is a kind of gauge transformation with complex value phase G. So under this transformation, Hamiltonian is mapped to Hermitian Hamiltonian H prime. And in terms of matrix spectrum, this is nothing but similarity transformation. Yes, the similarity transformation is a transformation with matrix S and inverse of S. So actually, this transformation does not change the spectrum of finite matrices. So under this transformation, the OBC Hamiltonian of the Hadamard's model is the spectrum of under the OBC is given by the spectrum of the Hermitian Hamiltonian H prime. So the spectrum should be on the real axis. So the spectrum is completely different from the previous one. And also the eigenstates and eigenvectors of the H of H prime is a kind of sine wave or the extended waves. And after applying the inverse imaginary gauge transformation, we can obtain the original wave function of the Hadamard model. And it means that all the eigenstates are localized at the one boundary because this exponential factor. So this is the simplest story of the non-Hermitian CFF.
Question.
Okay.
The transformations of C and C Baker are photo of independent. I mean, so why the G doesn't have the complex conjugate?
Actually, these operators are not in the Hermitian conjugation. Actually, in non-Hermitian Hamiltonian, the creation and annihilation operators are not in the relation of Hermitian conjugation generally. In non-Hermitian systems. But instead, the commutation or anti-commutation relations are still hold. So under this transformation, maybe I should write C bar, but actually I'm also interested in the matrix property here. So yeah, it does not matter actually.
But schedule now think is Baker as
Yeah.
G is just a number. G is a number.
D is a complex or maybe pure imaginary here.
A number, not function.
Not function. So,
G is pure real.
G is pure real. So it's a pure real. So the phase is pure imaginary. So phases are maybe maybe this is just
okay.
Yeah. So I is not pure imaginary, but side index. Maybe X is more appropriate. So this factor is not a phase, but amplitude line. So exponentially localized one button. So maybe easy X is more understandable. So maybe some of you might think, what is the difference between the non-Hermitian scheme mode and topological physics in recent topological, well-known topological physics? But actually, the edge states and non-Hermitian scheme modes are completely different in the following sense. The left eigenstate is localized at the different edge of the system. So, because in Hermitian physics, the left and right eigenvectors are equivalent to each other. So, Hermitian conjugate of right left eigenvector should be localized at the same boundary. But in the case of non-Hermitian CFF, they are localized at the opposite boundary. So, in this sense, non-Hermitian scheme modes and topological states are completely different. But sometimes the spectrum seems similar. So, but even in such a case, we can distinguish these modes by this criteria. So, in non-Hermitian topological physics, there are two types of boundary phenomena can coexist. the topological edge state from the one correspondence and non-Hermitian skin effect. So in the following, I will briefly review the competition between Hermitian topology and non-Hermitian skin effect. Actually, the Hermitian topology can also be defined in non-Hermitian systems. Maybe some parties discussed in Shozaku-san's lecture. First, I will consider the system with a non-Hermitian skin effect. The system, but the system is in the non-Hermitian case. In that case, the bound topological lines are defined in terms of momentum space picture. So, as in the case of the usual Hermitian topological layers, the first example is tutorial. So you can always add a constant dissipation, but you can define the topological space. More non-trivial one is maybe the bosonic BDG Hamiltonian. I will discuss it in the second talk. Actually, this bosonic BDG Hamiltonian has shear harmonicity and particle symmetry. So then you can define the topological invariant as in the case of the Hermitian systems. So here, for example, if you want to calculate the channel number, then the very connection is defined by using the usual right eigenvector and left eigenvector. So this is the non-Hermitian analog of very connection, and then the definition of the very temperature and the definition of channel numbers are completely the same on the Hermitian case. So only the difference is only in this wave function. So the such kind of topological invariants are discussed in a lot of papers. And now that these invariants are also constructed, maybe you can find such a topics in topological magnitude review. Other than non-Hermitian skin effect, the PVC information is not useful to discuss the topological imbalance, topological expansion because of the non-Hermitian skin effect. So this is a typical example. This picture shows the energy spectrum, the absolute value of energy spectrum for T is the model parameter. So one model corresponds to the one direction. This region is a topological region, and this zero means topological zero mode localized at the bottom. So this model is called non-Hermitian non-Hermitian sushi particular model. And so this is the topological region, but actually the topological so OEC gap closing point here is different from the PVC gap closing point. So this is very natural because PVC and OEC bar spectra are completely different. So, so you cannot predict the topological phase transition by using the PVC information. This is very different from Hermitian case because you can always predict the topological phase transition by only by using the momentum space topological value. And so So this is sometimes called the breakdown of boundary correspondence, but actually this is not the good terminology. And because you can always recover the boundary correspondence by using the OBC wave function to define the topological invariant. So the BBC should be BBC boundary correspondence should be defined for the boundary space under the same boundary condition. And the way to give the wave function is developed by Yam and Wang and Yokomizo-san and Martin-san in Tokyo Institute of Technology. And so here I summarize the method called non-local bound theory. First, the first step is analytic continuation from growth factor E of K, here K is the crystal momentum, to the general complex number Z. And the next step is very difficult, so I will skip the detail. But what we want to determine is the curve in the complex plane. So if you get a curve like this one, then it is called generalized Fourier, which is a kind of generalization of usual Fourier defined on unit circle. So E of K should be on the unit circle. So this unit circle is called is identical to the one-dimensional reactor. So if there is no shear effect, then the generalized Fourier zone is completely equal to the reactor. And the last part is constructing the topological invariant, but it is very trivial because the topological invariant is defined by the integration. But the only difference is in the contour of the integration. So anyway, you can define the topological invariant. And in the case of the Hermitian systems or non-Hermitian systems, we have
How do you define top OBC function? What's a top OBC function? Say for an Hermitian system, always right?
So maybe one answer is so maybe you can define the Hermitian scheme more. So maybe you can find the topological mode by this distinction, or also usually the Hermitian spectrum, band spectrum should be a continuous spectrum, and topological spectrum should be isolated one. Right? Sure. Maybe this kind of spectrum found in the non-Hermitian topological system. And these are the topological state localized boundary. And
the skin effect.
this is the skin. These are the skin modes in the energy spectrum.
And then start also skin.
these are also suffer from non-Hermitian effect, but there is also the topological localization. So these are the usually topological zero. Okay.
So, the no-box story that you showed. So, can you illustrate this for the other model?
Okay. So that is very actually the easiest generalized Boolean zone. So usually generalized Boolean zone is like this is about future, but usual one is like this, but another model corresponds to the circle, but the amplitude is less than or larger than 1. So
First of all, what would be your HLC for the other model? So, for the operation, the H as K equals H as X IK. That's in the Fourier transform the expression.
So in the case of patternless model, maybe E upon J times E by K. Now the combination is given by this one. Like this one.
So that's your H of Z.
Yeah.
And then next line, you say determine the being Z. So
one should use some difficult theory to
I'm just asking how to determine.
Here. This one. To enforce the open boundary condition and
So it's like solving some equations.
in general, if the open range is finite, then it is like a algebraic equation to solve that one. And usually the solution is very complicated in a complex way.
I mean, solution of what equation? So
Solution of
that model, do you equate that with E and solve it for Z?
so yeah, yeah, that's right.
Okay. So in that thought, that's you might use beta. Is beta the same as Z?
Yes, exactly.
Beta is Z.
So this kind of idea can be extended to, for example, higher dimension.
That's a very good question, but actually, so far there is no such a theory for general two-dimensional case because it's too difficult to solve the two-dimensional boundary condition. Okay. So in this context, the usual Hermitian topological boundary correspondence is actually the combination of the true boundary correspondence plus the fact that there is no scale. So we can reinterpret the Hermitian topological boundary correspondence. So the boundary correspondence in these non-Hermitian systems are essentially actually essentially from the Hermitian topology as discussed And in a non-Hermitian topological classification, this is called now known as linear topology. And in such a system, we believe that we can always define the correspondence in the previous test. So, for example, if the bar spectrum is like this one, and then if the non-Hermitian spectrum is deformed into the Hermitian spectrum without closing this gap and without changing the symmetry, then they are in the same phase in this sense. But actually, in non-Hermitian physics, there's another type of the non-Hermitian, another type of topological phenomenon. And actually, the conventional scale effect itself is a kind of topological phenomenon. So, in the point, I will explain this more for details. Okay. So, this question is very important. So, when does the non-Hermitian scale effect occurs? One trivial answer is to directly calculate the non-Hermitian spectrum. So this is the easiest way, and for the finite system. And for infinite system, you can still use the non-local band theory to determine the band spectrum. So in such a case, we can define the non-Hermitian scale effect if the generalized real zone is not already circle. But is there more any simpler way to find only whether the non-Hermitian scale effect will occur or not? And actually, the several observations indicate that the OBC spectrum cannot have a winding number. And actually, this can be proved. The second answer for this question is that the OBC spectrum cannot have winding number. So, not the winding number of PVC curve indicate the presence of the non-Hermitian scale effect. So, in the point, I will briefly explain our paper. Okay. So the collaborators are Professor Masatoshi Sato and Wada-san Shibata. And the related publication is this one with Professor Masatoshi Sato. And the claim of this paper is there are two claims in this paper. The conventional non-Hermitian scale effect is a kind of topological phenomenon. There are a lot of variants for non-Hermitian scale effect that the symmetry protected non-Hermitian scale effect or higher dimensional scale effect. Okay, so I will first consider the one-dimensional class A non-Hermitian, the correspondence between the one-dimensional class A non-Hermitian topology and non-Hermitian scale effect. Okay. So the purpose here is to compare the PVC and OBC spectra, but actually it is very difficult because while the PVC spectrum can be easily obtained by Fourier transform, the OBC spectrum does not have the simple analytic form like this kind of structure. And in such a situation, how can we find the relationship between the OBC and PVC spectra? And so the answer is to inside the semi-infinite system. First, I will discuss the relationship between the PVC spectrum and OBC, the PVC spectrum and semi-infinite spectrum. And the second step is to compare semi-infinite spectrum and OBC spectrum. And finally, we can obtain the relationship between the PVC spectrum and OBC spectrum. Note that all of these boundary conditions correspond to different, completely different spectrum. So first, I will compare the PVC spectrum and semi-infinite spectrum by using the index theorem. And actually, the second part is related to the imaginary index transformation I mentioned before. First, I will consider the one-dimensional pipeline Hamiltonian without orbital degree and with finite range copy. And if we impose a semi-infinite boundary condition, this is nothing but a Toeplitz operator in mathematics. And the spectrum of Toeplitz operator very, very long. According to the Toeplitz index theorem, the semi-infinite spectrum is equal to the PVC spectrum, together with all the points enclosed by the PVC curve with another winding number. The typical example is the completely asymmetric patternless model, or just for in mathematics, the shift operator. And Fourier class, by using the Fourier transform, you can easily obtain the PVC spectrum E of minus k, or just a unit circle. The spectrum is just a unit circle with winding number -1. And according to the Toeplitz index theorem, the semi-infinite spectrum is equal to the PVC curve together with all the points enclosed by the PVC curve. So this dense region should be in the spectrum. So this is very different from the PVC or OBC spectrum because they occupy it occupies two-dimensional region. This is very strange for people. And more complicated one is like this one. Interestingly, the region, this region is enclosed by the PVC curve, but the net winding number is equal to 0. So according to the Toeplitz index theorem, this is not in the spectrum. So this is the Toeplitz index theorem. Okay.
Maybe not so related. So this index theory kind of related to the Abelian singular index theory.
Maybe the simplest one. Actually, the Toeplitz index theory, there's different type of statement, and in that type of statement, it is very related to ideas in the one. But maybe the more simpler one. This theory, this is not the end of the theory. This part corresponds to the exponential localized boundary state. So again, in response to the simplest case, this one, the shift operator, and then inside the spectrum, so let us choose the complex number E inside the unit circle. Then this case E correspond to the exponentially localized boundary mode. You can easily check this one with the eigenstate of this Hamiltonian, because this is moving to the next one and the next one, and is we can obtain this one is the eigenstate. And also the absolute value of E is less than 1. So this mode is exponentially localized. And this type of theory is generalized to class A systems without symmetry. So mathematically, it is a kind of block techniques operator. But the condition for this theorem is very difficult. I don't know the exact answer, but here I simply know that the system has no extra symmetry. But such a system is called class A in topological physics. Actually, this story is maybe most of you know this theorem in other contexts. The boundary correspondence in one-dimensional system. To see this, again, let us consider the pattern-based model. And again, consider the KP vector. And here, KP vector can be reinterpreted as a zero mode of H minus E. And this is the boundary zone of this Hamiltonian. The crucial step is to use the Hermitianizing doubling process. So this technique is known in the non-Hermitian topological classification, or you can also use this one to classify the block-scale topological phase. But anyway, you can construct the Hermitianized Hamiltonian by using the original Hamiltonian and its Hermitian conjugate. This one is Hermitian matrix, but owing to this doubling, there arises an extra additional symmetry or chiral symmetry. And also, you can construct a new zero node like this form. Actually, this zero node is nothing but topological zero node class AC topological insulator. And if you choose the Hermann-Nelson model on the left-hand side, the corresponding Hermitian Hamiltonian is known as the Sushi Fahigano. It is very interesting for me because the simplest non-Hermitian CFF model is related to the simplest model for translation. So the index theorem about the spectrum is nothing but the topological boundary correspondence. So this is a half of the story. Here I compare the PVC spectrum and the semi-infinite spectrum. Next, I will consider the more important part, the semi-infinite spectrum and OBC, the relationship between the semi-infinite one and OBC one. And as you may expect, the OBC spectrum should be in the semi-infinite spectrum, like in this picture. So, in the point, I will briefly explain this for briefly explain. Maybe this one is very natural. The open boundary condition is almost can be regarded as intuitively open boundary condition can be regarded as semi-infinite boundary condition plus additional boundary condition at the other edge. But maybe mathematician will agree with that. So there is a gap, but I want to allow this inclusion relationship. But even if you allow this inclusion relationship, there is a question why the PVC spectrum should be shrunk. For example, why the PVC and the OBC spectrum is not equal to PVC1. Even in this picture, even for this picture, the inclusion itself should fall. But this is not allowed. Why? This is the next question I want to answer. So to answer this, so I want to omit the proof of this inclusion itself. The OBC spectrum should be semi-infinite spectrum. Because for this proof, we should first define the OBC spectrum in the infinite volume limit, but it's very mathematical. And because there's a gap between the isolated spectrum and continuous spectrum, mathematical. And in general, such kind of procedure is very mathematical and not physical. So I want to allow this inclusion itself. But once you allow this equation, you should also allow this equation, this inclusion. Because this one is defined by applying the imaginary transformation. And actually, this imaginary transformation preserves the translation invariance. So you should also allow this inclusion in the same level as this inclusion. And the crucial step in the form, the left-hand side becomes the original spectrum because as I mentioned, the similarity transformation does not change the finite matrix. Here, this one is finite matrix. So the left-hand side becomes the original spectrum. But the right-hand side is not equal to the original changing spectrum because of the infinite dimension nature of the matrix. So this is the crucial difference between the finite system and the infinite system. And actually, you obtain the new inclusion relationship for the original OBC spectrum. So this should be in the semi-infinite spectrum or the new semi-infinite spectrum. But under this transformation, the spectrum is deformed like this one. Actually, I did not specify the concrete form of the imaginary transformation. You can find another equation and another. So you can have the infinite number of inclusion relationships. And finally, we obtain the following inclusion. The OBC spectrum should be in the intersection of all imaginary gain transform semi-infinite spectra, like in this form. Now the proof is almost done. Let us consider the complex number E just inside the PVC curve. according to the Tetris index theorem, this KP vector should be localized, exponentially localized. So if you apply some imaginary gauge transformation, then this one can be playing with the new Hamiltonian. And this step is very important. And by combining this procedure and the new this procedure and this inclusion relation, the possible OBC region is iteratively shrunk by considering this step. So you can choose just E just inside the new perimeter, and you can find another one. And OBC spectrum should always be in this kind of spectrum. So the OBC spectrum should differ from the PVC one. And this step can be proceeded until the OBC spectrum has no winding. So the OBC spectrum cannot have the winding number because of the tendency index theorem. So this is a kind of explanation of why the OBC spectrum has no winding structure. Okay.
So in the previous example, you had a situation that you have a very complicated curve, such that there was a donut or so you cannot shrink any.
Yeah, that's right. But even such a case, by combining this one, the possible region should be shrunk because, for example, so maybe this kind of situation can occur, but if you consider the intersection, then the intersection should be narrowed under this procedure. So you can always shrink the intersection part itself. So even with complex case, you can at least physicists data. Okay.
So when you talk about a semi-infinite chain, so is there a difference whether it is wide semi-infinite and left semi-infinite?
Maybe different. So in that case, actually, but the direction of the direction of localization should be should be only 1 or 2. So maybe depending on the winding number, actually the boundary type is changed implicitly now. Actually, so
the other question is that if you mentioned that in the under OBC boundary condition, then there is no winding. But is this always true? I mean, even if you extend your non-Hermitian system with more parameter, for example, if you consider third next to nearest neighbor topic.
at least for finite range, then at least the templates index theorem holds, then I can be generalized, then this statement should hold because of the presence of the region with winding means in such a case we can shrink by this procedure. So the non-zero winding number means always we can treat this. We can use this procedure. Okay.
Maybe we need the previous question. So in the semi-infinite boundary condition, all your states are most of them are localized on one side. And then you're applying the space transformation. Is it correct that among some of those localized states, by having this exponential space transformation, some of them will become localized state on the other side, like exponentially make it bigger, right?
So that is very, maybe I cannot explain in English, but too maniac. So actually, eigenvalue is not, eigenspectrum is not equal to spectrum in mathematics. Actually, I implicitly assume that I consider the eigenstate, but for depending on the winding number, you should also consider the you should switch the right and the left eigenvector. So the statement should be modified in such a case. Actually, but this is for not for the complicated version. So actually, yeah.
So this is different from the H state H state on left and right. Are kind of different. Now in the skin effect, the left and right eigenvalues, the right ones are localized in your left part, and the left eigenvalues, the eigenstates are localized on the opposite side. So
yeah,
even starting from the one boundary, those states can be mapped to situation with two boundaries on the left and right.
yeah. So if the winding number is negative, you can use the eigenstate of semi-infinite further, right eigenstate. But if the winding number is positive, then it should be right left eigenstate. So this is a slight difference, but I omit in this presentation actually.
So based on your argument here, the shrinking occurs when there is a non-trivial sample of imaginary transformation. But for example, in the other ways, but is there always such non-trivial imaginary transformation? Or
Yeah, of course. But so in the case of the Hadamard model, the shape of the semi-infinite spectrum is like this one, very beautiful way. But in the case, this is not equal to the after imaginary transformation completely, then the OBC spectrum, you can find the OBC spectrum by using only one imaginary transformation. But in this kind of case, sometimes for some imaginary transformation, this one is determined, and for some other imaginary transformation, this one is determined. And finally, we can obtain this kind of mode, but you cannot have the easy correspondence between the PVC and OBC1. So, yeah, it's. So there is no simple material transformation to obtain this spectrum. But in the Hamilton case, we could. Okay.
So to previous yes. So is the OBC spectrum could be seen as a fixed point on this spectrum formation?
Fixed point.
Fixed point of this kind of edge transformation.
Yes.
Fixed point. Maybe I didn't have the.
What's the definition of this?
So actually this corresponds to this kind of cusp point. You mentioned about this point? No?
I think he's asking whether we can see the OBC spectrum as a fixed form of the edge transformation.
I guess you write the definition or the answer there. The question is that fixed point of G. So below plus. There. Yeah, this one. So this expression, if you wanted to say that this fixed point of G, applying random G to your spectrum, you get some spectrum. That the fixed point of random spectrum. If you want to
Maybe I can answer here. Sorry. Okay, so this is a short summary for the first part. The skin effect is a kind of class A condition phenomena, and that can be derived from the experiment using the imaginary transformation. Okay. Next, I will consider some correspondence between some non-Hermitian or the generalized non-Hermitian skin effect. In modern topological physics, functional topological physics, the quantum Hall effects turn out to be an example of the more general concept, the topological insulators or superconductors, are also known as symmetric protected topological phase. Now, in Hermitian topological physics, the conventional skin effect of the class A phenomena might be an example more generalized notion. So I recall in our paper we call such a skin effect as a symmetric protected skin effects or the higher dimensional skin effects. So maybe the higher one is more trivial. But I will first discuss the one-dimensional one. Okay, for that, in the following, I will consider the time reversal symmetry frame with fermionic one. And actually, there are two types of non-Hermitian time reversal symmetry. And here I will call transport type symmetry because in non-Hermitian matrices, the transpose node is not equivalent to the complex conjugation. So at least there are two generalizations of time reversal symmetry. And even in that case, we can define the Coulomb degeneracy at the same complex energy E. But eigenfunctions are different from the complex type symmetry. So you can construct a Coulomb pair by using the left eigenvector. And in 1 and 2 dimension, the Hermitianized Hamiltonian corresponding to the class DC topological superconductor. In 1 and 2 dimension, this kind of Hamiltonian is classified by these topological index. So if we consider the non-Hermitian scheme mode that corresponds to the class DC topological superconductor, we may obtain the V2 scheme effect by using the correspondence between the double Hamiltonian and non-Hermitian systems. So in the following, I will briefly summarize the one-dimensional case first. The scheme effect occurs with Coulomb degeneracy. So here the Coulomb degeneracy are defined in this time reversal symmetry. And actually, this kind of time reversal symmetry is arises when you consider the effective Hamiltonian of the range function that can be defined called the range function. So maybe this symmetry is very natural. So owing to the time reversal symmetry nature, there are two scheme modes in the relationship of the Coulomb sphere. But if you copy this system, this means that the topological number is equal to 2, which is equivalent to 0 under this periodicity. So the scheme effect can be suppressed by adding the symmetry preserving perturbation. So this is a V2 nature. And final one is about the symmetry protective nature. Under the infinite volume limit, even an infinitesimal symmetry breaking perturbation can destroy the scheme effect. So this is a kind of symmetry protective nature. And the correct one is the limit is this one. First, you should use the infinite volume limit, and then use the infinitesimal limit of the perturbation. So this kind of physics is also known in the physics of symmetry breaking. So this kind of topic is discussed in this paper. Mentioned that infinitesimal instability of the spectra against the perturbation.
So okay. Hermitian system, we say trigger phase, there's a potential zero more or bumps A state, and what do you mean by C phase breaks?
So the right right eigenvectors are localized at the different AT.
Let's say for emission system, G non-trigger G2 is non protected zero mode. I mean, in the energy state. Now you have a complex eigenvalue. What's the
so there's no restriction for the energy in this case. Just so because this time reversal symmetry enforces no condition for the spectrum, actually. But the corresponding Hamiltonian has a symmetric condition for the energy spectrum. But corresponding non-Hermitian system has no such a symmetry for the spectrum itself. Okay. So more non-trivial effect is over in the two-dimensional case. This is a model for these effect in two dimensions. The model consists of the Dirac forms with Barry-Independent dissipation. So actually, the double Hermitian Hamiltonian or this block Hamiltonian correspond to the topological superconductor. So in two dimensions, there are two directions for the open boundary. So I will pose two open boundary condition in two direction or okay.
Sorry, is gamma matrix?
Sorry, this gamma is just a constant, but the momentum dependent.
That's some
So spectrum is this one corresponds to the graph point, and this one another graph point. Maybe in total there are 4 graph points, and depending on the graph point, the dissipations are different. So, but even by just adding the constant in terms of matrix,
It's the Pauli matrix ready and then dissipation or just proportional to the identity matrix.
this one is proportional. So, finally, under the full open boundary condition, we want to expect the non-Hermitian scheme effect. But unfortunately, nothing happens for this boundary condition. Well, if you are familiar with topological physics of Majorana zero mode, then the answer is very clear. Actually, the double Hermitian topological superconductor has no exact zero under the full open boundary condition. So instead of the exact zero mode, under this full open boundary condition, quasi zero modes appear. So they have the finite gap proportional to 1 over system size. So in that sense, these quasi zero modes only becomes exact zero mode in infinite volume limit. So what I have shown in the previous slides was the correspondence between the topological exact zero and non-Hermitian scheme modes. In that sense, this correspondence cannot be applied for the quasi-zero. So this is the reason why we do not observe the non-Hermitian scheme effect in that case. So, but so in such a situation, how can we realize the two-dimensional non-Hermitian scheme effect? If you are familiar with Majorana physics, the answer is also clear. Using the topological effect. So, so let us consider double Hermitian Hamiltonian with pi class. This corresponds to the class D3 topological superconductor with pi class. And so actually, in the physics of Majoranas, it is well known that under the insertion of the topological effect, the Majorana, in the case of class D3, the Majorana double localized the topological effect of the pi box here, and the other Majorana modes are localized at different places. So this is a mechanism for this mechanism can also be applied for the physics this scheme effect. And actually, we can obtain the two-dimensional time universal symmetric this scheme effect under the full open condition with pi class. This is a non-Hermitian scheme mode, localized at the topological effect and boundary. And this is the structure. Actually, this scheme effect is very different from the conventional one. First, only order of L eigenmodes in order of L square modes are localized. So these ones are not these scheme modes, and the other ones are bad modes. Okay, then scheme modes are separated from the bad modes because this is different from the Hermitian topological Hermitian Hermitian mode. So these are maybe actually this is separated, but yeah.
What do you mean by separated?
So if you consider the infinite volume limit, then the spectrum should be like kind of separate. And moreover, the localization is in the radial direction. And localized at the surface and defect. So this is very different from the conventional one. Okay, so maybe. So this is a summary of the first law. Okay.
So you even the PSS is A1 here. So if you have two boundaries and it is finite size, I guess your H state, the energy would be not be zero, but even the simple SSH model. So
Sorry,
So in the case of D2, you mentioned that the open boundary case, the whole Hamiltonian, because H state is not really zero mode, but has some small energy. Exponentially small energy, so you don't have H state.
so you mentioned about the exact thermal, the difference between exact and plus thermal.
Then doesn't the same argument apply for the A1 scheme?
A2, as E2.
The same argument of C2, but doesn't it apply to A1 scheme?
Plus A2.
Same.
So maybe the difference in exponential localization and one-over localization. Maybe, yeah, that's a good question. Actually, I do not know the answer, exact answer. So, but actually, they are completely different modes. But I do not have the exact answer. Sometimes, yeah, sometimes I try to understand that difference, but I do not have knowledge to distinguish it exactly mathematically. But the fact is that the order or one, no one, so the fact is that the correct zero mode is and exact zero mode are the terminology that topological physics. Topological is about physics. Maybe the specialist in such a field know the answer, but I don't know.
So in non-Hermitian systems, we have two kind of classes. One where we see skin effect and where we don't. So from the perspective of symmetries, can we classify these two classes of system?
So
one with skin effect and one without.
that may be difficult. There is no complete answer.
So right now, the way we understand is there are the systems where we see skin effects, and there are systems where there is not, like there is no classification. As of now. As of now, we don't understand the classification. This is what you are seeing.
So maybe I want to say that there is no complete understanding for the correspondence between the classification and the scheme.
Maybe I don't get if I find the left state and right state, his state, they are on inside, and you can say this is a topological region. So I can say that this is a topological state. If the left kid and right kid, they are open system, they are local inside. And this is some topological region. So are they topological region? I say that's what I say. If I find the left angle kid and right angle kid, they are localized at different stage, then there's a topological.
But in this case, there.
Only for D2 or
But in class A scheme effect, you can also have both sides instead, because if the field is spectrum has a winding number plus one minus one, and the corresponding eigenvalues are like all these items, say localized at Y and Z. So in such a case, different, they are localized at different places. But there is no relationship between these two modes.
So, for online audience, anyone question? Okay, if no, let's close this section and we start at 3:30. Thank you, speak again.
This is the second part of today's talk. So next time we consider the application of the condition C in dissipated bosonic variable oxygen or BDG system. So this topic is based on the current paper and something published. It's okay. So this is the outline of the second talk. I will first consider the bosonic BDG system without dissipation. And interestingly, even without dissipation, the bosonic system can be related to a non-Hermitian problem. And after that, I will focus on I will discuss the particle Hall symmetry in the dissipated bosonic BDG system, as well as introducing the dissipated bosonic BDG system. And okay, so let's start the first part. Usually, non-Hermitian systems requires dissipated or open quantum nature. However, the bosonic BDG Hamiltonian is a kind of exception. So, in the second quantization, BDG Hamiltonian itself is Hermitian operator. So the system should obey completely the unitary dynamics. The BDG Hamiltonian is written in terms of the quadratic form of the bosonic annihilation and creation operators. In this kind of space is called number space or number representation. This Hamiltonian matrix is still Hermitian Hamiltonian matrix. And this is a completely same as the superconductor case, but the difference comes in the explicit representation of the BDG Hamiltonian. Here, small h is a Hermitian and small s is a symmetric matrix. And this, as in the case of fermionic BDG systems, S represent the particle number violating term, A or AA, as in the case of fermionics, as in the case of superconductors. So, and actually, if a particle number violating term is present, so S is non-zero, then the excitation spectrum is related to non-Hermitian eigenspectrum. So this is very strange because the Hamiltonian itself is still Hermitian. The important point is that the energy spectrum is not equal to the eigenspectrum of BDG Hamiltonian itself. So to see this, let us consider the diagonalization of the BDG Hamiltonian matrix itself. by unitary matrix U. Because BDG Hamiltonian matrix is Hermitian, you can always diagonally it by using the unitary matrix. Now, this is a transformation. New bosonic operators are defined by using the matrix element of unitary matrix U. Here, large N means the number of degree of bosonic degree of freedom. So the total system is described by 2n by 2n Hamiltonian matrix. And so as in the case of fermionic BDG systems, the creation and annihilation operators are described in terms of the all creation and annihilation operators. But new bosonic operators do not obey the bosonic commutation action. So this property comes from the bosonic commutation relationship. So this comes from the commutation. This side from here, you cannot obtain the identity operator. So this Bi and Bj data do not obey the bosonic commutation relation. And actually, in the case of fermionic BDG systems, this problem does not happen because of the anti-commutation. Because of the anti-commutation relationship, this sign does not arise. So you can always reduce to the U data form, and then you can always obtain the identity operator, which means that these fermionic operators obey the fermionic anti-commutation relationship. This is the difference. So the difference between both of the fermions, the summarized in this time. And so unitary diagonalization is not appropriate for the bosonic systems. So instead of the unitary diagonalization, we should consider bosonic variable transformation defined in this form, P and P data field, Hermitian conjugate P. So this is very similar to the diagonalization, but actually this is not a mathematical diagonalization, because the mathematical diagonalization is defined by using the matrix and inverse matrix, not complex conjugation of other Hermitian conjugation of P. And here P is not unitary, so P complex Hermitian conjugate is not equal to the inverse. So in general, so in that case, this bosonic variable transformation is not a mathematical diagonalization, but still the combination of P data H P becomes the diagonal matrix. So they're similar to diagonalization, but owing to the symmetry inherent in the BDG Hamiltonian, actually the diagonal elements contain the two copies of the original energy spectrum, what we want to know. So this is the bosonic variable transformation, and actually this P should obey the para-unitary condition, not the unitary condition. But if the particle number violating term is absent, then the P and sigma Z should commute. In such a case, this condition is reduced to the unitary condition. But in general, if the particle number variability in term is present, then this is not equivalent to the unitary condition. And this is the story of bosonic Fourier transformation. And actually, this problem can be related to non-Hermitian eigenvalue problems. To see this, let us consider a new Hamiltonian matrix sigma z H. So I will call it H sigma B Z. And this one can be diagonalized by this matrix P. This can be easily checked. In the second equation, I use this property P inverse sigma z is equal to sigma z P dagger. So and in the final expression, I use the Fourier transformation and becomes this one times this one is equal to lambda minus lambda. And this form is very similar to the fermionic BDG Hamiltonian case. And here I will summarize the property of the sigma BDG. Firstly, there is pseudo hermiticity that comes from the hermiticity of the original BDG Hamiltonian. So you can check this one by very straightforward equation. So this is the good property of the sigma BDG Hamiltonian. And second one is more non-trivial, the particle Hall symmetry. So as in the case, this form is very similar to fermionic exactly the same as the fermionic BDG symmetric, fermionic particle Hall symmetry. This can be also trivially proved, but you should use the explicit form of the BDG Hamiltonian, and you should use the property of H and S. So finally, you obtain the fermionic particles as fermionized particle Hall symmetry, but this is important. The important point is that actually other than this pseudo hermiticity, one can also consider the different type of particle Hall symmetry. And actually, this new particle Hall symmetry is defined by the transpose, not the complex conjugation. These are the at first sight, these symmetries are different, but under the if we assume this pseudo hermiticity, this can be easily derived from this one by using the trivial calculation. And this can also be derived from this one. So these are equivalent to each other under this symmetry. So actually, this is very interesting for me. And eigenspectrum of the Hamiltonian, eigenspectrum of sigma BDG is takes real or complex number is pair, complex conjugation pair, lambda conjugate. Okay, so the energy spectrum or the eigenspectrum is very important if you want to consider the stability or instability of the bosonic system. There are two types of instabilities in the bosonic BDG system. First one is known as lambda instability. In the lambda instability, negative energy leads to thermal instability in usual complex matter, because the nature prefers the lower energy or the ground state energy. But if there is negative energy excitation, then the ground state is should be collapsed by such a negative excitation. So that means that the ground state we assume was wrong in such a case. But even in such a case, if the system is isolated, then such a negative energy is allowed, because the isolated in the isolated system, lower energy should be allowed. So such a system is considered to be realized in the whole system. So this is a kind of exception, but in usual complex matter physics, the negative excitation means that thermal instability. More crucial instability is the dynamical instability. So if this eigenvalue lambda is complex, then lambda or complex conjugation of lambda should have a positive imaginary path. So as you may know, such a positive imaginary path leads to the exponential growth of the fluctuation. In that sense, the ground state should be collapsed by the fluctuation. So this is called dynamical instability. So basically, these two types of instabilities are present. So this is the basic story of the bosonic BDT system without the dissipation. Before closing the basic part, I want to mention the non-Hermitian particles for symmetry. In non-Hermitian physics, transpose is not equal to the complex conjugation. So there are two types of generalization of particle for symmetry to non-Hermitian systems. But as I noted, under the pseudo-hermiticity, the complex conjugate and transpose are equivalent to each other. So then the natural question arises. In the absence of dissipation, in the presence of dissipation, the pseudo-hermiticity is absent, because the pseudo-hermiticity comes from the unitarity of the system or the hermicity of the Hamiltonian. But so if the bosonic BDT systems are dissipated, which one is the appropriate part for symmetry? So this is very non-trivial question. Transpose type is okay, or complex conjugation type is okay. So maybe it's very non-trivial. In the following, I will answer this question. I will first answer this question in terms of the Green's function formalism. By the way, the answer here is only for the Green's function formalism. So I did not mention the general one. But if you want to consider Green's function effective Hamiltonian, then it may be true in general. So next I will discuss the particle for symmetry in dissipated bosonic bosonic BDT system.
So questions.
Okay.
So you start with, you begin with a permission operator, permission Hamiltonian, but you end up with a non-permission. I just wonder what's the physical meaning of this particle states created by this molecular operator P data. Is that the particle in the usual sense?
Particle what?
In the usual sense, I mean, what's the physical property of this single particle states created by P data?
That actually that is related to the ground states squeezing, let's say. So the states are very similar to the superconductor BCS wave function. And B and B daggers correspond to the bosonic bosons. Maybe this is not answering. I don't.
Coherent state.
Yeah, coherent state. Or the squeeze, more generally, squeeze state. Squeeze states are corresponding to the BCS wave function of the two bosons. But maybe I can. Maybe this is not very answer. And so, first I so the non-Hermitian Hamiltonian can be introduced in the condensed matter community in terms so there are several ways to introduce the effective Hamiltonian in condensed matter systems. But here I will focus on the wave function formalism because it is very traditional one. So as you may know, the poles of wave function matrix correspond to one particle energy of the one particle energy of the quasi-particle. So the typical form of the wave function is given by this one. Here, small h means the non-interacting Hamiltonian matrix, and sigma r means the self-energy. This sigma r is usually non-Hermitian. Then the total matrix is non-Hermitian matrix. And if the self-energy does not depend on omega, or the omega dependency can be ignored, then this one can be the spectrum of this matrix describe the poles of the wave function. In such a case, we call this one is non-Hermitian Hamiltonian. So this type of wave function appears in the fermionic or bosonic systems without particle number violating terms. Or you can also find this type of wave function in fermionic BDG system. Or you can also find classical systems such as classical photonic systems, photonic crystals, or the harmonic oscillators, classical harmonic oscillators. Next, I will consider the bosonic BDT case. This is slightly different from the usual gradient function because of this factor. So the difference is in the first term of the denominator. So instead of the identity operator, this term is proportional to sigma z, where sigma is parametrics in random space. So this is the only difference, but owing to this factor, the force are given by the zeros of omega minus sigma z h, not all of the omega minus h, as in the usual case. So this is very interesting for me because the structure of bosonic Bogorelov transformation, the sigma z times h, that is naturally arising in this system. So this is very surprising for me. Now you can define the new Hamiltonian by the combination with sigma z times h plus sigma r. So this is a new effective Hamiltonian. And note that there are two types of non-Hermiticity. One is from the boson particle number violation, or the bosonic BDT nature. And the other is from the self-energy part, or dissipation, or that is part of dissipation, the coherence, or the dissipation, the coherence, or interaction. So, okay, so now we have the relationship between the wave function and the effective Hamiltonian matrix. So, if we want to consider the symmetry of this one, it is good to consider the symmetry of wave function itself. So, next, I will consider the symmetry of wave function.
So how does sigma z arise in second? Yes. Sigma z.
Maybe sigma z times sigma z.
One. Yeah, how does it arise? Related to the G0 inverse.
Yeah.
So L is a anti-complicated.
So determinant of the denominator separated by this one.
So G0 is the function for
So question again.
G0 is a great function for
So Z.
yeah.
This one.
Yes.
Maybe I can answer the question in the next slide. So you mean why Z0 should be?
Yes.
Okay.
Yes.
That's the question. Okay. Maybe I can answer this one. So this is a definition of the wave function in random space. Maybe you can find this kind of knowledge in traditional textbooks such as with molecular or I don't know. But I think there is a non-equilibrium range function method. And so the only difference from the usual retarded and advanced range function is comes in the this part. This is the non-spinner that consists of the A and A dot. So you have the 4 components. And so maybe to answer this question, I should consider the symmetry of boson liquidity system. So okay, I will proceed. And so there are four components in the regarding grid function. And also in advanced grid function, there are 4 components. And in total, there are 8 components in grid functions. But these 8 components are not independent each other. So, and actually, you can check this by hand. These four relationship between DR and the ABCD. For example, this one, the DR IJ TD prime becomes is equal to AA JI T prime T. So R is equal to A and I and J are flipped and T and T prime are flipped. And this is by definition. And all of them are easily checked. And the important point is the next step. But because I want to consider the omega dependent form, I will enforce the time translation invariance. So this means that physics is in the equilibrium or is in the steady state. So under this assumption, we obtain these 4 relations. So this transpose comes from the group of I and J, and I is equal to A, and D is A, D becomes A, and the minus sign it comes from the group of time T and T prime. And by combining this equation and this relation, so the retarded grid function is the Hermitian conjugate of the advanced grid function. And by combining these equations, we obtain the explicit form of general grid function formats. So now you obtain a general form. I did not assume anything except for the time translation invariance. So this is quite general. And now we can easily obtain the particle symmetry of bosonic grid function in space. So if you consider this symmetry, this omega sigma z is you can check this omega sigma z is the correct one in the denominator. And maybe in the non-preserving case, this kind of equation should be solved due to this this relationship. So now we have the particle symmetry for grid function. So
how do you get the star instead of constants?
This one.
Oh, I see, I see. I see.
Ah,
That we have function is maybe the ones we have.
Actually, the important point is that we could separate the R and A, and we could erase the C and D. Yeah. Okay. So the general form is given by this one. And actually, we know the relationship between the green function and the BDG, sigma BDG Hamiltonian. Then, by combining these properties, we can obtain the particle Hall symmetry for the sigma BDG systems. So, but note that this form, it depends on the omega dependent. This is the omega dependent form, and actually, this omega dependence is very important in the following discussion. But first, I will ignore the omega dependence. So, if we ignore this omega dependence, then the correct symmetry is given by the complex conjugate type symmetry, not the transpose type symmetry. So this is the answer for the previous question. Which one is the correct particle Hall symmetry, the complex conjugation or the transpose type? So in the absence of the hermiticity, then complex conjugation type is natural symmetry. And here the hermiticity of the BDG Hamiltonian is absent. The constraint for the energy is only from the particle Hall symmetry. So PH's counterpart is given by the minus E conjugates. So, this can be easily checked by the Fourier equation. Maybe this is all. Here, I will use the complex conjugate type symmetry. And anyway, we obtain the particle symmetry. And as in the case of the non-dissipating Hamiltonian, the positive imaginary part means positive means dynamical instability. Okay, so next I will consider omega independent self-energy. But this assumption is actually very non-trivial in the cosonic BDG system. And I think, actually this is just my opinion, I think that in non-equilibrium aspect should be always required for the omega independent dissipation if we want to BDG or cosonic BDG problem.
I'm sorry, I got lost. So in the previous case, you mentioned there are two options. So now what is the answer? Which one is preferred?
This one.
I'm sorry.
Conjugate type.
I see. Okay. And the other one is
Transpose.
okay.
So yeah. In the following, I will assume this symmetry because this should always fall. But here I drop the omega dependence, but this assumption is very non-trivial. Yeah, only I will explain. So omega independent self-energy is enable us to consider non-Hermitian Hamiltonian dynamics, because in usually we want to erase or ignore the omega dependence because of simplicity. But such approximation is not valid in thermal equilibrium, or because omega independent self-energy is very unreal in the following sense. To see this, let us consider the diagonal dissipation. Diagonal means in number space. Actually, this small sigma r omega should be 0 if omega is negative. Because if there is a dissipation under the negative frequency, then it means thermal instability. So sigma r omega should be 0 for the negative omega. So this kind of so the bus thermal bus state should be over the positive energy. So in thermal equilibrium, self-energy strongly depends on the sign of omega. This is very trivial because for positive omega, the whole part should be 0. While for negative omega, the particle part should be 0. This is the frequency, not mass. Actually, the symmetry depends on the which one we choose. So omega is in the green function method. Omega is a kind of energy. What we if omega is less than 0, the bosonic case, then the state should be absent in that case. Yeah, that is the reason. So this is a condition from the lambda to avoid the lambda instability. So in thermal equilibrium system, this should also should always hold, but maybe I don't know the general case, but at least for the this kind of quadratic bus, then the bosonic bus, then we can always say such a thing. So in this sense, to approximate dynamics by non-Hermitian dynamics, then the sign dependence should be removed. And one answer is answering called out existence, but it's very it's a kind of exception. So here I want to consider the periodic driving, or also known as colloquial formalism. Actually, in colloquial picture, the notion of the energy makes sense only when you're driving frequency large omega. So it means that one can introduce a kind of energy shift between the bus and the state For example, let us consider this simple case, the system state and the bus states. And if we introduce the dynamical coupling between the bus and state, then driven by this frequency, then these states are coupled to each other, and you can shift the energy in this direction. In this sense, the so you can consider the sign. You can get rid of the sign dependence of the frequency in this sense. And actually, this kind of idea was maybe originally used in the quantum optics. So the idea is almost the same, but in such a systems, the terminology blockade was not used. Instead, usually use rotating wave approximation. But for example, let us consider the dissipating decay model. Decay model is defined by the one photonic mode and one large spin. Or you can, or in quantum optics, this consists of the a lot number of atomic two-level systems. By combining the lot of two-level systems, then we obtain the largest systems. So, mathematically, this is just one spin, but the spin is very large. And if we consider, if we introduce a Einstein remarkable boson, or also known as spin wave, or semi-classical approximation, this one becomes the new bosonic operator, like Shiba C dagger or this such kind of. So this Hamiltonian can be regarded as a bosonic BDG Hamiltonian in that semi-classical picture. And this is the story of the decay model. And if you introduce a dissipation, then the model is dissipated decay model. And the dissipated decay model is defined by combining the Hermitian R plus dissipation, constant dissipation kappa, or also known as Markovian dissipation. But as I noted in the previous section, in terms of the BDG Hamiltonian, this kind of dissipation is very non-trivial. Actually, they also use the periodic driving in order to obtain this kind of effective Hamiltonian. And they use the so-called rotating wave approximation. Actually, the photons, real energy of the photon is much higher than the energy of Einstein remarkable boson. But by applying the rotating wave approximation, the effective photonic energy is lowered. And also, the photon is coupled to the photonic vacuum with some temperature. And this temperature is much lower than the photonic energy. So the photonic vacuum states, there is no distribution in this region. But for the photon, there is negative energy dissipation and constant self-energy with respect to this photonic energy level. And by applying the rotating wave approximation, omega, then these energies are lowered here. And this corresponds to the Bloch like energy shift. So, anyway, this type of omega independent self-energy is a realistic approximation in this sense. Okay, so finally, I will discuss the boundary dependent dynamical instability by non-Hermitian skin effect in the above context. In the following, I will assume the symmetry of the BDG Hamiltonian and Bloch gliding type dissipation in principle. Again, I want to emphasize that the course of grid function determines the stability or the instability of the system. The typical example of again the dissipated decay model. This is the spectrum of the dissipated decay model in classical picture. So the number of eigenvalues are 4. Corresponding to the Holstein-Riemann boson and photonic degree of freedom and the particle symmetric degree of freedom. So in total, there are 4 eigenvalues, and all the zero coupling between the photon and Holstein-Riemann boson, then the state energy does not have the positive imaginary part, but by increasing the couplings constant between the photon and the Holstein-Riemann boson, then there's a transition point to get the positive imaginary part. So, important point is that the instability, the non-Hermitian spectrum is very important to determine the phase transition or the instability. And moreover, the instability can be induced by the combination of the 2 non-Hermiticities. One is from BD's nature and dissipation. And note that I did not use the amplification, just dissipation. But the combination of BD's nature and dissipation effectively act as a amplification. Okay, so this is the basics of the instability, dynamical instability. And next, I will consider skin effect. But by using the skin effect, one can construct an OBC stable and PBC unstable model. So to see this, first I will consider the simplest model. In the diagonal term of the BDG Hamiltonian, I will use the Hamiltonian model, and in the diagonal part, I will use the particle number minority term, which is proportional to the identity of the element. So dissipation is included in the only included in the diagonal form of the BDG Hamiltonian. Okay, so identity and note that the total Hamiltonian should obey the complex type particle force method. And this alpha is just introduced for the stability of the system. So let us consider this type. Let us consider first the dissipation only. Then the parameter is set to be such that the PDC spectrum does not have positive imaginary part. So the PDC and OBC spectrum have no positive imaginary part. But if we introduce a finite particle number violating term, then the spectrum, PDC spectrum, has the positive imaginary part. So very small but positive. So in this sense, the OBC spectrum is stable, but PDC spectrum is unstable. So in this sense, the instability depends on the boundary condition. So this is very strange, but the intuitive interpretation for why this happens is the following. And actually, this part corresponds to the left mover of the in one-dimensional in terms of the one-dimensional chiral ball. And this one, maybe this one, the right corresponds to the right mover, and left mover is amplified, but right mover is very damp. So under the periodic boundary condition, because there is no obstacle for the left movers, then the left mover is exponentially amplified. So the system becomes unstable. But if we introduce the open boundary, then the left mover is amplified until the boundary. And then after the regression, it becomes the right mover, which is very damp. In that sense, the exponential amplification does not occur in the under open boundary condition. So this is a kind of intuitive explanation for the boundary dependent dynamical stability. Okay, so finally, I will briefly calculate the steady state accumulation under open boundary condition. For model with boundary dependent dynamical stability, actually the OBC steady state shows a kind of exponential particle accumulation. So to calculate it, I will consider non-equilibrium steady state Green's function. But for application, momentum independent dissipation, as in the case of Hatana's model, is very unrealistic. So I will consider the momentum independent dissipation because that is more realistic. So in the point, I will consider the spectral winding without non-zero without momentum dependent dissipation. So this is a trick. Let us consider the particle number preserving part. Instead of the hyperless model, I will consider this model. So this shows the kind of spin momentum locking. Sin k is g plus this one, and combining this Hamiltonian with spin dependent, but momentum independent dissipation. This combination acts as a effective spectral winding, effectively momentum dependent dissipation. So it can reduce the effective spectral winding number. The spectrum of this system is described by this one. The PVC spectrum has a winding number, but OBC spectrum is collapsed. And the total BDG Hamiltonian is given by this one. And so here this one is just a constant shift. And these ones are the spin dependent dissipation and particular vibration part. This is a final slide that I will skip the detail of the non-equilibrium Green function. But I should mention that this type of lesser self-energy does not depend on the momentum. So that is very important. So and actually this kind of dissipation is useful to the decay type dissipated decay model. So maybe this form is very natural, I think. And the spectrum is like this one. So the PVC spectrum is unstable and the OBC spectrum is stable. This is a particle number accumulation. Actually, this is a long graph. This graph shows the exponential accumulation. This is a reminiscence of the dynamical instability. So, okay, so this is the kind. So this is the summary. Thank you.
So in the last part, you given several examples for the topological jump for sigma individual. But what kind of spin model would be represented by this type model, or write the Hamiltonian using speeds?
Speaking magnums.
Or how do you start with spin model, like a Heisenberg model, and assume some ground state and consider the fluctuation around it?
So actually, when I was a PhD student, I tried to implement the spin momentum locking in the Lagrange systems. Maybe it can be. But maybe the to implement such a Lagrange spectrum, we need complicated classical structures such as triangle lapse or lapse rated one.
Maybe some complicated lattice.
So collinear structure. Well, Jaroszewski-Moyer type. Yeah, actually, the Jaroszewski-Moyer interaction can be acted as like so. In one-dimensional system, this kind of structure can be introduced, and Jaroszewski-Moyer interaction acts as a Rashomon interaction in electron systems. Very similar, but this is mine.
Let me say, marginal system of Hermitian phonic system with quadratic interaction. The Hermitian is served with many body Hermitian that are really
Many body Hamiltonian is Hermitian.
yeah,
Yes.
and so the spectrum should be here.
Yes.
And yes, but to derive this spectrum, we have to use H sigma BDG. Yeah, so you mentioned some instability, lambda instability. Yeah, so your first point is if there is no such kind of instability, eigenparts. Yeah.
Yes.
I see.
Eigenvalues are positive.
Positive. I see. And in the red section, you want dispersion or
Yes.
Then this kind of which phenomenon
Yeah.
that you
Actually, someone tried to induce the non-Hermitian scale in isolated order center. So they are the negative yes, but the system is Hermitian without dissipation. So in such a case, there very one can construct the toy model that shows the skin effect, but we should break the we should suffer from the lambda instability in such a case. So I mean this kind of energy. This is the particle part and this is the whole part. This if we allow the negative energy excitation, and actually in the coordinate system, in isolated systems, one can use this one, or can grab this one. So in such a situation, we can also construct a non-Hermitian scheme model, but maybe irrelevant for user for this one.
Is this spectrum in boundary condition of PDC or OBC?
This is what we have. So
I have a stupid question. So in reality, which boundary condition should we use?
so for the OBC, the spectrum is like this one, and for the PDC, this kind of spectrum appears in their construction.
So if you need even open boundary condition, we may have some.
But that instability is rather instability and not dynamical instability. So because of the absence of the positive equation up, so that is stable in some sense, but very
Yeah, so related to this question, yeah, what is the frame of your third or fourth part of this contour? So in reality, we should employ probably open boundary condition.
yeah.
But in open boundary condition, there's no, you said there's no instability.
Yes.
Yeah, so
yeah.
yeah.
So what I will say is more exponential localization. This is very, maybe,
But it doesn't deviate to instability.
yes,
It's
yes,
just
that's right, that's right. So in that sense, this model is also a kind of toy model. but in usual condensed matter, except for the isolated, completely isolated case, then lateral instability is essential. Lateral instability should be avoided.
Physics in the field is not really correct. Instead of stability or just just a different patient. So, I mean, you should you can control the Hamiltonian in that condition, and you can ask for to have a positive measure but that's a controllable system. So what we need is stable. Also, you can control a non-static non-emission Hamiltonian and create a positive imaginary energy. Say that the system becomes unstable.
Yes.
You need to see the system grow up or something. Maybe that's controllable.
So if in that case, the ground state should be lost. In another, for example, the ground state is in general condensate. In the case of boson. In that case, the system becomes in a different state. Maybe related to the so I don't know, but maybe the correction appear, but I don't know what kind of. Because actually the semi-classical analysis is just a linear analysis of the non-linear gross beta x equation or other such kind of bosonic equation. So the BDG is just a linear analysis. So what we cannot expect, we cannot derive the ground state there after the phase transition.
I don't understand why you have to find this omega independent self energy. Like if we have like a system against your self energy, and you said it's probably omega dependent, you respect symmetry. I think a normal situation, your self energy would be like positive when omega is positive, and negative when omega is negative. So good function. And when omega is zero, the self energy is zero. But I think it's okay.
Yeah, but
You can think your proposal.
just I want to consider. Just one, I want to, just the non-Hermitian people want to reduce the non-Hermitian Hamiltonian. That is the problem. Research. But you can consider non-omega dependent theory, of course.
And for this energy, like for ion omega, you have a gigantic self energy, and not dissipation, and some force pressure. And the Green function there. I think that's more natural than to
Yeah.
about
But I do not know we can construct a dynamical instability in such a case because the theory may be difficult. Okay, so just because if you want to define the excitation there, you should solve the determinant of like this one. So and here omega comes in, and the excitation problem is one should analyze with the analytic continuation to obtain the complex energy spectrum, because this should be replaced with Z. And actually, we can show the symmetry for this complex Z.
I guess what you should do is, so that's what you do in static system. So here it's a frequency dependent problem. So I guess what you should do is to Fourier transform back to time, and then see if there's a exponentially. So not using that criteria, but criteria after going back to here.
So you mean the real-time calculation?
Yeah, which has some information from your.
Yeah, that's one way to process our problem. Yeah. So maybe just I wanted to make the omega difference because of the non-Hermitian people.
I'm right here. Audience, do you have any question? Let's close this lecture. Okay, thank you everyone. And thank the speaker and also our friend center. Thanks for joining. Okay. For speakers. Thank you for coming here, and also thank the online audience. Thank you very much, and have a safe trip home. There's iPhone. Okay, see you around, and we'll have another interesting summer.